Welcome to demo video 4 in our course B09 using R for AI. We're going to talk about a very basic supervised learning model using R. So what we're going to think about is using AI-ready data that's artificially created here for simplicity, and it's quite a small data set with limited features, um, purely for the purpose of implementing some very basic supervised learning model. We're going to split this data into 80% training and 20% testing. Then we'll use machine learning to link the relationship between the features and the labels at hand. And what we know as well is that the labels at hand are not necessarily good, are not necessarily ideal in terms of they're effective in the sense that they're independent from each other. So each contributes towards the model. Common models that might be used are linear regression, which is what we're doing, decision trees, support vector approaches as well. That might include sort vector regression, polynomial regression, and so on. And what we're trying to infer is the capacity of it to take the test data and correctly pick the labels um, based on the training data. So we're going to split our data in 80% training and 20% training. That's the common way. We'll use the initial split function, and that uses simple random sampling. If there's more complexities to our data set, for example, um, there's potential biases within our data so that simple random sampling may not be effective. We might split that into groups that we then subsequently merge using using simple random sampling within each group, and then merge them to ensure that we have appropriate representation within our different subsets of data. For example, if our cases are very rare and controls are very common in a human population, that could be a common approach. So I'll make an R-split object and use the training and testing functions to get info about these data sets just to see how different they are. And then alternative approaches could use stratified sampling. So if we had other types of data, such as time series data, we could use initial time split to ensure that we have representation at each of the time points and they're not biased by under or over sampling particular time points. We also have the approach using testing and training and validation approaches, which is to use the initial validation split approach where we have 20% allocated to validation as well as 60% for training and 20% for testing. This uses the validation function to check the validation set. So our goal here is to use the initial split to split the population data by strata, so we can use the training function on that and check the number of rows that are present before we proceed to looking at what we get. So let's move over to the R script now to get a better feel for what we're doing. So here what we can see is a quick summary of different R functions that allow us to apply types of regression in R. There's quite a lot of varieties. GLM, generalized linear models, is probably the most common one. And here we're going to use a form of that to make predictions using our model here. So we're going to use the initial split function to split our data and then check that we are training and testing data contain the relevant number of rows that we sought, which is 1600 for the training data set because we have 2000 samples. Our testing set is 400, and then we can check the numbers of S and L belonging to our class that they're balanced, which is great. That's what we want. So then we consider if what could arise in a data set if we did not stratify that sample. And then also note that the step normalized function uses the training mean standard deviation to transform the test set. Why not compute the mean and standard deviation separately for the test set? What would be different about that? Note also that we are able to use here the recipe function. So we're able to use the recipes package using creating a variable called micro recipe, where we predict the outcome based on the diameter, the growth rate, and the zone using the training data. What we're doing that is to step normalize all the predictors, which means that the levels, which are where we have the growth rate and diameter and zone, are all intrinsically different. We subtract the mean value from each of the values divided by the standard deviation, so the scales of each of the features is relatively similar. If we look at the structure um, of micro recipe. We can see inside there is a lot of data inside there, including the original data as well as the normalized data that we want to use as well. So this data gives us the steps that were implemented, and it assesses the number of variables by role, um, and means we can move on to the next step of using prep and bake to estimate the parameters like standard deviation means from the training data. So if we used prep on our micro recipe and look at the structure of prepped, we can see that it has the um, relevant data inside there, and we use the bake function then to get the first few values that are present. And what you see is that the scales of each of the data are comparable to each other. If we look inside prepped directly, um, we can see that there's different components inside there. So we can use bake to extract that information. So if we look at the structure of this function, we can therefore plot a histogram of this data, and we see that scaled around 0. If we change that variable to zone underscore mm, we can see that's centered around 0 as well. If we did that for growth rate, again, that's scaled around 0. So you can see that they're all standardized, which is great. So now we can use Parsnip to look at the model more carefully. And here we're looking at logistic regression using the GLM function. Um, I'm using this for classification into two groups, S and R. So we can look at the output that's stored in the variable LR spec. So we can see there that shows the engine and mode, not the coefficients yet, because we haven't added them to this model yet. So what we can do is update our workflow using the workflow function. So to create a workflow variable where we add the micro recipe into it, and add the model for the LR spec, and check our output from there. So we're saying that we're using GLM to do regression, and then we've one major step so far. What we can do then is take um, our micro WF variable, specify they're looking at our training data and to create fitted values based on that. So what we can use is the extract fit parsnip and pyd functions to create a table from this data where we can see the intercept, sizes, the growth rate, diameter, and zone. We can see their values relative to the standard errors, so they're all pretty large and comparably large, and they're all good predictors of the output. If we just leave out the tidy data parameter, we can see more details on the model. So we can see things like the degrees of freedom, and things like the AKE-INK information criterion as well. And now we can make predictions based on the test data set. So we're taking our fitted model and we're looking at the new data as the test data. We're going to bind the columns to predict our data as probabilities, um, and check how well it worked. So our code worked in terms of looking at the 400 samples in our testing set, and we have our predictions for whether they're in the S or R categories. And we have this across all the samples. And what we're doing is creating a confusion matrix based on the predictions where we have the truth listed as well, where we're looking at the predicted class. What we see is that 189 are susceptible and are classified as such. 11 are not and are classified as resistant, and vice versa for resistant. 11 are misclassified and 189 are correctly classified. What we can also look at is the key metrics for this, such as the accuracy, sensitivity, specificity. We can do this across all of these ones using the metrics set function, where you have the matrix correlation coefficient and the F1 score as being ones we might want to predict. So then we can take metrics out and produce metrics for this. And you see the MCC, which is probably the best bias, the best predictor here, is 0.89. The F1 score is 0.95, and the same for the other values there. So you got to get a better sense of our output. We can create a ROC curve using the ROC curve function. So we take our predictions. The truth is the outcome here. We're specifying as pred S because that was the first that was listed first in our vector. And we're using the autoplot function to add on the plot labels and the plot size. So there we can see our ROC curve. So we're holding the area under the black line. It corresponds to how good our model is. So for the vast majority of things, it is classifying things well. And then we can also look at the area under the ROC curve directly. It constitutes 99% of the area, which is quite good in some. And what we see here as well is that we're using pred R as our value and using event level to specify that we're looking at the second event. So for example, if we change this to pred S, that will also give us 0.99. If we overfit this, we're taking our entire data set, our fitting using our entire data set and then make predictions on this and get the area under the curve for that values. Typically that will be higher. It isn't in this case because the random sampling and the tiny differences between the testing and training data set. But typically if we just use our entire data set, we'll find that we are overfitting our data. So that kind of covers what we wanted to look at. So we use the functions initial split, training, and testing to split our data into the training and testing data sets and to check that they were okay and it was completed correctly. We use the recipe function and step normalize function to process the data and standardize it so that no single variable would predominate the prediction outcomes. We use prep and bake to also to fit the parameters as well. We used logistic regression and the workflow functions to and fit in Parsnip to create and track our predictions. And then you evaluated it using the metrics that we mentioned, the confusion matrix, and the area on the curve using the ROC functions as well. If we want to go further in this, we use cross validation or other methods such as regularization when you have many predictors as well. That's what we would look at next. So that completes our demo video. Please check out our next course on B10 Python for R as well.